Good evening. Let me welcome all of you here this evening to this very special event. I'm Jim Plummer, the Dean of the... Is the mic on? I think the mic may not be on. No. Temporary delay. So.
How many engineers?
Is the mic on? Okay, great. So let me start over again. Welcome to this very special event tonight. I'm Jim Plummer, the Dean of the Engineering School here. And not only do we have a full house here in NVIDIA Auditorium, but this is being webcast to several hundred of our alums, actually all around the world. And so we welcome all of you who are watching through the power of the Internet, which is what we're going to talk about tonight. So we're here tonight to honor Dr. Vint Cerf as one of the inaugural School of Engineering Heroes. The Heroes program here in the School of Engineering is a program which recognizes individuals who have made great technical advances that make human, social, and economic progress possible. Our heroes embody really all of the attributes that we take as part of our mission here in the School of Innovation. It's the School of Engineering. Innovation, entrepreneurship, great teaching, great research. So we look for heroes who embody these things in the way in which they guide their lives and the contributions they make through their careers. Vint joins actually a distinguished group of 7 other engineering heroes in the inaugural group, and these are people whose names you will recognize: Fred Terman, William Hewlett, Dave Packard, Charles Litton, William Durand, Ray Dolby, and Don Knuth. And so the 8th person is Vint Cerf. Now, unlike many awards, all we ask of engineering heroes is that they tell us how they would like to spend a day at Stanford in the engineering school, or more generally at Stanford. And when we talked to Vint about this, he said, "I'd like to spend some time with engineering students." And so we did that this afternoon. He said, "I'd like to talk about some of my ideas on the future of the Internet." And we said, terrific, that would be a great thing to do. So here we are tonight to listen to Vint's ideas about the future of the Internet. Those of you who are here live, when you go out the back of the auditorium, you'll be able to see just to your right, when you go out, there's a wall actually that has plaques with the Stanford Engineering Heroes on it, which you can look at. And those of you watching over the Internet, you can actually view it on the School of Engineering website. Those of you who are not here on campus tonight, I'd really encourage you at your earliest convenience to come and visit the new Science and Engineering Quad of which this building is a part. This building and this quad have really transformed the School of Engineering and the Sciences at Stanford. They're remarkable physical places which have created a home for us which is welcoming, which allows for our students and our faculty to work together, to collaborate, to do things which just simply weren't possible in the previous facilities that we had in the School of Engineering. So please come visit and see the remarkable new home that the School of Engineering has. Now let me just say a few words about Vint Cerf, although I think all of you probably know much about his career. He received his undergraduate bachelor's degree in mathematics here at Stanford, and then he went to UCLA where he got his PhD degree. Following that, he actually interviewed for a faculty position here at Stanford, and I was amused over dinner to hear him tell the story. He may tell it again, but he was telling some of the students and I over dinner that when he interviewed for the faculty position here at Stanford and was actually offered the faculty position, he turned Stanford down because he didn't think he was smart enough to teach Stanford students. So fortunately, he was convinced that that wasn't the case, and so he did accept a faculty position here at Stanford. Subsequent to that, he went to DARPA, the Defense Advanced Research Projects Agency, where along with Bob Kahn, he did much of the fundamental work which created the Internet. The TCP/IP protocols and the basic architecture of the Internet were developed while he and Bob were working together. Their work was recognized by President Clinton in 1997 with the U.S. National Medal of Technology. And in 2005, Vint and Bob received the highest civilian honor bestowed in the U.S., the Presidential Medal of Freedom. And this medal recognizes the fact that their work on the software code used to transmit data across the Internet has put them, and I'll quote, "at the forefront of a digital revolution that has transformed global commerce, communication, and entertainment." Subsequent to his work at DARPA, Vint went on to lead technology advances at MCI and took and then a break to return to research at the Corporation for National Research. He was the founding president of the Internet Society and was on their board until 2000. And he's a fellow of all of the societies that you might think: the IEEE, the ACM, AAAS, the American Academy of Arts and Sciences, the National Academy of Engineering. Currently, however, he has probably the most interesting title of almost anyone I know. He's a vice president at Google, but his more relevant title is that he is the chief internet evangelist at Google, which is an interesting title. I think it describes what it is that he does. And it's also, I think, a very fitting role for an engineering hero. Please join me in welcoming Vint Cerf.
Thank you. That was amusing. Let's see, Willy Wah, despondency, and holy cow, what am I got myself into here? So problem number one is getting this thing back into, there we go. Well, first of all, it's quite an honor to be labeled a hero, and I'd like to suggest to you that's probably not the right nomenclature for this kind of recognition. It's my view that things as big as internet don't happen because one person or two people did something. It's because a whole bunch of people decided that they wanted it to happen. One thing I've learned in my career is that if you can convince a whole bunch of other people that they want to do this, it makes the work a lot easier. This is the Tom Sawyer Effect. And so those of you who are in engineering and you're wondering, how you should organize yourselves for a successful career, learn how to sell. Don't look down at the salesman as some, necessary, thing. Selling is very important. Convincing other people that they want to do what you want to get done is a super important way of leveraging what you're trying to accomplish. And so, if anything, I think maybe some kind of catalytic award would be appropriate. I did want to announce that Nick McCune, who is involved in the clean slate work here at Google, at Stanford. Where am I? At Stanford, along with Guru Palakar. Nick was just promoted into the National Academy of Engineering as a fellow, and I'm sure there'll be announcements about that, but it just came out today, and I'm pleased that that's happened. Because Stanford, of course, is where the basic internet design work was done. And now we're seeing Stanford engaged in looking at what alternatives there might be in a clean slate. What happens if we were to start over given what we know about the history of the net. I have to tell you that my focus tonight is on kind of the network aspect of internet, not so much on the application space. And so if you were hoping that I was going to tell you secrets about what Google is planning to do, I don't plan to do that. I'm not going to be too deep into application space, although we will touch on a few things. But mostly I'm thinking about the basic internet and the mechanisms that drive it and the things that we could do to make it a lot more interesting, a lot more effective, a lot richer as an environment. So with that warning in mind, let me take you back into history. That's assuming I can get this thing to... Okay, gang, this isn't behaving terribly well. There. Okay, so I'm going to take you back 40 years ago. This was the original 4-node ARPANET. I was at UCLA at the time. Bob Kahn was at Bolt, Beranek, and Newman. I was around with other folks at UCLA receiving the Sigma 7 computer from what was then Scientific Data Systems. I think this was number 4 off the production line. That was the host that we put into the Network Measurement Center that Leonard Kleinrock ran. I wrote the software to connect the Sigma 7 to the first IMP, interface message processor of the ARPANET. Then a month later, in October, the SRI IMP was installed. Don Nielsen, who's in the audience, wave your hand, Don, please. There he is. He was there at SRI when the second node was installed. And the other two, UCSB in Utah, were done by December. So we started with this little 4-node network. And the Sigma 7, of course, is in a museum somewhere today, and some people think I should be there too, but here I am. If you fast forward, this was a very successful experiment in demonstrating the concept of packet switching. Len Kleinrock showed the mathematics behind it, showed what the queuing theoretic models would tell us about how packet switching would work. But this was an implementation to see whether or not it would actually function. This network had a backbone speed of 50 kilobits a second, blazing, 50 kilobits. So if you fast forward a few years, you get to an internet that looked like this. This is an automatically generated chart taking the global routing table and associating a color with each autonomous system that's made up the collection of networks that are the internet. So it's important to notice, first of all, that there are many autonomous systems. Second, that the network itself is not top-down driven. It is not, there's no central authority that makes decisions about the internet. This is a grand collaboration. And once again, I want to emphasize how important the collaboratory nature of this system has been. People build pieces of internet and connect them together. They do this on a voluntary basis. They observe the standards that are developed also in a very open and collaboratory way in the Internet Engineering Task Force. So what you see is a network that got bigger, got more colorful, and it got more connected, and that's as good a description of the internet as I can think of right now. It has grown in every dimension. Things have gotten bigger by factors of 1 million. The number of hosts on the publicly visible internet has grown over time. It's now past 700 million, but it doesn't take into account things that are episodically connected to the net. So laptops, desktops, mobiles, and things of that kind are also part of the net environment, plus machines that are hiding behind firewalls that are part of the enterprise environment. They're not necessarily visible to the public. So this is simply a lower bound on the number of things on the net. The real numbers are probably in the at least 1 billion or 2. If we look at the number of people on the network, as of the middle of last year, there were slightly under 2 billion estimated to be on the net. And I'm sure that's an undercount because there are people who make use of, more than one person may make use of a machine in an internet cafe. There are a lot of people on mobiles that have been internet enabled. I don't know what the percentage is. It's probably 15 to 20% of the mobiles have internet capability. So as time goes on and more mobiles become internet enabled, more people will be online using the internet's assets and resources. That's an important thing for Google because we're trying to offer products and services to people who use the internet, and many of them are going to use it for the first time and possibly forever using mobile devices, whether it's literally a mobile or a netpad or something related to that. So we and you who might be trying to serve a similar population need to take that into account. Here's where the people are, at least as of the middle of last year. You'll notice that Asia has the largest absolute population of internet users. Half of those are in mainland China. These statistics, of course, would have looked quite different 10 years ago. Europe is another almost 500 million people. Look at the penetration percentages in the population. In Asia, it's only 21% on the average. So when they get to 70 or 80% penetrated, the numbers, of course, will be well over 1 billion or 2. In Europe, it's 58% on average penetrated. Of course, it varies depending on the northern countries are more heavily penetrated, up in the 75% range. The southern European countries somewhat less. Of course, I've given up giving any predictions about Europe because they keep adding countries, so the definition of Europe keeps changing. So I don't know what to make of that. North America used to be the largest single population of internet users, and plainly it is not anymore. We're already 77% penetrated within our North American population. So our numbers are not going to get much bigger in absolute terms. To the extent that we have any influence as a community on internet, it will not be because of our numbers. It will be because of our inventiveness, our creativity, our enterprise, our capability to create and grow new companies. The rest are, as you see in this chart, Africa is by far one of the biggest challenges to bring internet into use there. And of the then estimated 110 million in the middle of last year, I would say they are dominated by the 150 to 250 million mobiles that are already in operation in Africa. So once again, we get a clear sense that mobiles are an extremely important avenue for internet growth. Bob Kahn started the Internet Project, and he had been thinking about this prior to his arrival at ARPA. He was very much involved in the architecture of the ARPANET, the predecessor system. And so he began thinking about the notion of autonomous networks that could be interconnected. And he said that if we were going to be successful in this enterprise, that we couldn't assume that we could make changes to every network in order to make it part of the internet. We had to take the net as it was and figure out how to integrate it into this linked system. He also had the very bright idea that the communications would have to be on a best effort basis. Now, why would he have come to that conclusion? It was because some of the networks he was already contemplating didn't have a lot of reliability in them. A radio-based system could experience interference. You could lose a packet just because of two things transmitting at the same time. Ethernet, which had been invented in 1973, had the potential for collisions and the need for retransmissions. And so it too had a kind of best efforts character to it. Satellite-based systems were similarly at risk. And so even though the ARPANET was a highly reliable system, the other networks that joined the packet family didn't necessarily have that characteristic. So Bob recognized that and said that best efforts communication would be the right target for us. And that meant that the failures in the net had to be recovered on an end-to-end basis. And so that was very much a part of the philosophy. Since the networks were not designed to interwork directly, we had to stick something in between them that would pretend to be a host on both nets and then pass data back and forth. We called them gateways because we didn't know we were supposed to call them routers back then. Cisco coined the term router, if I remember right. There would be no global control. Now remember, this is the military that's pursuing this. Bob is by this time at DARPA. And the notion here was that we didn't want any central control in the net, because if there were a central control, that would be the place that people would attack and the communication system could be disabled. So we wanted this to be a highly distributed environment. We knew that because each network thought it was the only network in the world, that meant it didn't have any way of expressing, send this to another net. So we had to invent a way of saying, send it to this net and to that computer on that network. That's what internet addressing was about. I'm not going to go through every single one of these things, but the whole point here is that there were an array of requirements that showed up. One of the things that was not a requirement is that the network support any particular application. So this is one of the big lessons for me, is that you don't want to overspecify a system like this. You want to give it some characteristics like best efforts communication, end-to-end recovery, some kind of flow control, the ability to route through multiple networks. But we didn't assume any particular application. And because of that, it was eventually possible to put a variety of applications on the net that, as the network got more powerful and got faster, could be supported. So the packets of the internet didn't know how they were being carried. They didn't know if they were on a satellite link or an optical fiber or a radio link. And they didn't know what they were carrying. All they knew was that they had a little bag of bits they were supposed to carry from point A to point B with some probability greater than 0. That's all that it had to do, and everything else, we would try to recover on an end-to-end basis. So the result of this ignorance of carriage, what it was carrying and how it was carried, has allowed people to build virtually any application that can be transported as a chunk of digital bits. So that's how we ended up with voice over IP and video conferencing and email and all these other things. The layering that we encountered during the ARPANET design carried over into the internet. It had the nice property that if you could maintain an interface that was stable and assume that the upper layer would rely on the underlying layer for some functionality, if you kept the interface stable, then it didn't matter how you implemented the underlying layer, as long as the interface was kept the same. So the stability of layering really helped a lot, because the internet kept ingesting new technology, new transmission media and the like, without visibly changing some of its key interfaces to the rest of the upper layers. And that was a very important feature of the internet and the ARPANET architecture. I was also very proud of the fact that when we decided on the global IP address space, we did not bind it to any country. And my rationale for this was pretty simple. I thought, if the military is going to use this, first of all, it never knows where it's going to fight. And if you had country-based IP address allocation, can you imagine being in conflict with country B, having to go to country B to get address space in order to have the fight with them? And, my first reaction was, that ain't going to work. So maybe we better just have a topologically significant address space and not one that has any direct binding or control by any particular national entity. So those things, I think, contributed greatly to Internet's success. Open source and openness in the development of the Internet was equally important. The Linux, actually even earlier, the Unix-based TCP/IP was a very important part of the story because it was freely available from Berkeley. Lots of people used it. Sun Microsystems relied on that for their workstations. Xerox's Ethernet, so what eventually came out at 3Com, for example, were widely available. And those things, together with the easy access to TCP/IP implementations, accelerated the rate at which the Internet was adopted. The other open sources that you see today, like Chrome and Chrome OS and Android and so on, are equally important to enabling people to build and operate pieces of Internet. I think the most dramatic thing about the World Wide Web is not necessarily its functionality, but the fact that if you were in a browser and you saw a really interesting web page, you could say, show the source HTML of that web page and then copy it if you wanted to, or change it and try things out. So people learned to be webmasters by inspecting other people's HTML code. And once again, that really accelerated the ability of people to participate. Bob and I also consciously decided that there would be no intellectual property claims about TCP/IP. It was not patented, it wasn't constrained, it wasn't proprietary. And we did that for a reason. We knew that at the time we were doing the work that networking capability existed. IBM had SNA, Digital had DECnet, HP had DS, but each of those was proprietary. And if the military were to purchase IBM or DEC or HP machines, we didn't want them to be trapped into a proprietary networking protocol that would prohibit them from being able to buy anybody's computer and make it part of the system. So we thought there had to be a non-proprietary open standard for that. And we said if we made any intellectual property claims, then people might resist adopting it because why not? You have your own proprietary thing. Why should I bother with this other thing that I have to license? So we said no licenses. It's completely open. What's really remarkable is that this work was being done in the middle of the Cold War. And here we were releasing this stuff to everybody around the world, whether it was the Russians or the Cubans or anybody was free to take it. And I'm sure if we'd asked at the time whether it was okay to do that, we would have gotten a different answer. Nobody asked, and we were under the radar. So I don't know if we could get away with that today, but we got away with it then, and it was a very important element in the success of the system. There were some commercial drivers which helped a great deal. When Cisco, the founders of Cisco realized that the way the academics were making routers was to get a computer and a graduate student and wrap the graduate student around the computer and turn it into a router. And that worked fine, except that you ran out of graduate students. So Cisco and the others, like Proteon, started to build equipment that they could sell to the academic community. Then I got permission around 1988. This is after the Internet was launched in 1983, January. I got permission to connect the then Internet, NSFNet in particular, to MCI Mail, which is a commercial email service. This was to break a policy barrier that said the government backbones were not allowed to carry commercial traffic. And you could understand the rationale for that, but I thought if we could break that barrier, we could demonstrate to the commercial community that there were, in fact, reasons to want to sell service as well as equipment to the commercial business world. So we got permission to do that. And as soon as we announced that the MCI mail system was connected to the Internet, the guys at CompuServe and Telemail and all the other commercial email suppliers said, wait a minute, those MCI guys can't have this special treatment. We want to get onto the Internet too. So we said, fine, go ahead and do that. And then much to everyone's surprise, because every one of these proprietary and independent email systems, which had never talked to each other before, could talk to the Internet. They could talk to each other through the Internet. The result was we interconnected all these commercial systems that had never been connected before. So it was one of those really nice outcomes that I hadn't actually thought about it up front, but it's a way of breaking through a whole lot of commercial barriers that allow this kind of interoperation. Well, there are some changes. By the way, I'm sure some of you who are tracking this stuff know that the Internet Corporation for Assigned Names and Numbers, which is responsible for allocating Internet address space as well as managing the domain name system, has recently allocated the last two of its /8 16 million address chunks to the Asia Pacific Network Information Center. They have 5 additional chunks. They're called /8s. They have 5 additional chunks which are now automatically to be released to the regional internet registries, of which there are 5. So basically, the Internet Assigned Numbers Authority at ICANN is out of IP version 4 address space. That doesn't mean that the network information centers or the regional internet registries are not out yet. But they will probably run out of available v4 address space sometime between the last quarter of 2011 and sometime in 2012. That doesn't mean the internet stops working, but it does mean it gets harder to grow. You can imagine trying to sell somebody a mobile phone and saying, it's a really lovely phone, it works, it has great stuff. I don't have any telephone number to give you, so you can't make any phone calls. But apart from that, it's a really good, instrument. So if you're trying to sell internet service to somebody and you say, it's really a great service, I can't give you any internet addresses, but, apart from that. So we clearly need to do something, and the internet community has done something. In '96, it's a standardized IP version 6, which is 128-bit address space for format for packets on the net. Unfortunately, it doesn't interwork with the 32-bit IP version 4. And this is, I'm embarrassed to say that I was at DARPA at the time that the 32-bit 4.3 billion address space was chosen, because nobody else was making any decisions and I couldn't get the project to move on. So I said, okay, after arguing for a year, it's 32 bits. It's enough for an experiment. 4.3 billion addresses. I mean, the internet hadn't even been built yet. It was 1977. So I said 32 bits should be enough to do the experiment. And if it works, we'll do a production version. Well, it's 30. It's 30 years later, and we're running out of the v4 address space. So the production version is IP version 6. So those of you who are in any position to implement and cause v6 to happen, please do so before we completely run out of v4, so we can run, dual mode for a while to get through the transition. There are other things that are happening. In fact, let me just skip forward to some slides here. That's the exhaustion thing. Another thing which has recently happened is that the domain name system, which up until now has been written in Latin characters, can now be written in a number of other scripts: Cyrillic, Korean, Japanese, Arabic, Hebrew, and so on. So domain names in the country code space are now being allocated in these non-Latin scripts. And in addition to that, ICANN, again, the organization that manages the domain name system, is also opening up for what we call generic top-level domains that could be written in Latin characters or in non-Latin characters as well. This is quite a big change to the domain name system. It opens up some risk factors because there are characters in one language that look like characters in another. If you think about Greek and Latin and Cyrillic, you can imagine some good examples there. But the coding of those different scripts is different, so the computer sees a Cyrillic A is different from a Greek A, even though they look the same to the human eye. There are risk factors associated with confusion. On the other hand, when you think about people who would like to express their domain names in their native languages, you can't escape the desirability of being able to do that, so that's happening. There are all kinds of security problems associated with the net. Some of them are just annoying things like spam, but they have the effect of potentially overwhelming email or consuming a great deal of transmission resource that is being wasted. Or there are propagation of viruses and worms and Trojan horses and things like that. There are denial of service attacks. I mean, there's a long list of issues, and not all of them are technical. Some of them are stupid things that we do, like picking bad passwords. Like, how about password for your password, which is what some people do. Or you pick names that you can remember, but you can find them in the dictionary, and you can do reverse dictionary attacks against them. Or our operational people get flustered when somebody calls and says, oh my God, the system's falling apart and I'm the systems engineer responsible for this and I can't remember the password for so-and-so and the whole world's falling apart and can you help me out? And maybe they will have mentioned the names of a few people that you might know, and you get persuaded that this might actually be a legitimate request, And so you hand out the password, and of course the world comes to an end. So teaching people not to react that way and to be very suspicious about anyone who seems to be demanding information that they don't necessarily deserve is a very important thing. But actually the worst security problem, as far as I'm concerned, has to do with this last bullet here called spectacular human error. Anytime you try to configure something, it's easy to get the configuration wrong. And sometimes it's obvious that you have a bad configuration because it involves a parameter that's the wrong value. It's out of range. But sometimes all the values are within range and they look okay, but they have the side effect of cutting off half of the internet. Now, we had an example at Google once where when we crawl the net, we try to look at the websites to figure out whether or not they might have malware, and we make a little notation that that website might have badware on it. And then if someone using our search engine actually pulls up a choice to go to that web page, if they click on the hyperlink, we actually put up what we call an interstitial page that says, we don't think you should go there. There might be malware that would harm your computer. Of course, you can still go there if you want to, but we're trying to warn people of that. Well, there's this automatic table that gets generated as we crawl through the net, but it is manually editable. Okay, so somebody went in to do some manual edits to add something or take something out, and they stuck a slash in the wrong place. And the slash was interpreted as every site on the internet has malware. So no matter where you went, you got this little red page saying there's malware out there, you probably don't want to go there. Well, we discovered that pretty quickly. There were lots of people say, what the hell? WTF. So, we fixed it within probably half an hour or something. But it's an example of the kind of spectacular configuration errors that people can make, and we still haven't figured out how to solve that problem. Detecting a bad configuration is a really deep semantic problem, and I don't have good solutions to that. There are other reasons why we have such serious problems. We have operating systems that are willing to be invaded and penetrated, and that happens all the time. We have browsers that are naive about what they do. In the early stages of the internet, when you downloaded a web page, it had HTML in it that described the format of the web page, it had some imagery and some text, and that's about it. There wasn't too much damage that could be done. But now, not only do we have HTML, but we have JavaScript and Java and Python and other high-level languages. And some of the browsers just, download the home page and they just interpret everything that's there. Some of the browsers are running at a very high level of privilege in the operating system, which allows them to store stuff in the operating system or on the disks, which amount to Trojan horses and viruses and worms. And the consequence of that, of course, is what's called drive-by downloads. You just go to a website, and just by looking, you've downloaded and infected your machine. So there are this long list of potential hazards that arise, partly out of technical problems and weaknesses that should be remedied, and partly out of practices that are not attentive to security. There are privacy problems, too. And although many of them have to do with technical flaws and weaknesses, penetrations and the like, an awful lot of them are by doing silly things like leaving your laptop behind somewhere, or losing a memory stick that has sensitive information on it, or even bad business practices where you accumulate information that one would consider private, and then you decide that you're going to share it with somebody even though that really hurts somebody's privacy. That's just a bad business decision, but we are all affected by such choices. And then there are invasive devices. We today carry around things that can take pictures, can do videos, can detect location. There's quite a bit of information that people can produce. And then if you go to places like Flickr or Facebook or other things and you see an image that's up there, you can identify it by tagging it. So we live in a world now in which it is harder and harder to achieve any kind of privacy. And I'm not even suggesting that I know what the right solution is to that. All I can say is that if privacy is your concern, this is a hard problem to crack. So once again, I think we have to rely on policy and business practices and maybe even legal constraints to protect people's privacy, because technology is not necessarily adequate to do that. Now, I wanted to quickly mention that cloud computing has become a very big deal everywhere. Google and many others are involved in that. If you're interested in a good dissertation topic, interaction between clouds is a great topic because we are today in 2011 where we were with the internet in 1973. We didn't know at the time exactly how to interconnect distinct separate networks to each other. And in the cloud environment, we don't quite know how to interconnect the clouds. We're okay with the client-server stuff. I mean, you can push your information from your desktop or your laptop into a cloud and you can pull it back out. But suppose you want to get data to go from cloud A to cloud B. Well, Cloud A and Cloud B don't even have the ability to say, hi, I'm Cloud A and I'm trying to reach Cloud B. There's no vocabulary for that. It's just like the internet address space. If it didn't exist, there was no way for one net to refer to another. There aren't any good ways for clouds to refer to each other. And moreover, if the data in the cloud is access controlled because you only want certain people to see it or interact with it or edit it, if you want to move that data to another cloud, you have to move the metadata that will protect that information, and we don't have a vocabulary for doing that. So, and now imagine trying to do simultaneous computations with two clouds interacting with each other in real time. None of those tools exist. The vocabulary doesn't exist. The standard protocols and formats don't exist. So there's a lot of space here for research and experimentation, and I'm excited about that. Well, this leads me to observe that there are all kinds of research problems that are still fresh, despite the fact that the internet design is well over 35 years old now. We don't have standard Erlang formulas, for example, that we use for telephone system, or have in the past used for telephone system design. How many lines do I have to install at this building in order to make sure the probability is less than 1% that you won't get a dial tone when you pick up the handset? Mr. Erlang figured out that the average phone call was about 3 minutes in a nice bell-shaped curve, not counting teenagers. And so that was applied to figure out how many lines you had to get to run a reliable and responsive telephone net. We don't have Erlang formulas for the internet. Part of the reason for that is that we have too many different applications of the net that don't have such simple statistics as the telephone statistics are. So in the core of the net, you get some fairly standard results because of the law of large numbers. Lots of traffic being brought together in the core gives you some stability, but at the edges, the dynamic range is huge. You could be clicking on something, and then 2 seconds later, you're getting 150 megabit per second file transfer. By the way, the Erlang formulas are wrong for today's teenagers. They don't talk on the phone at all. They don't want to talk to each other because they're scared to talk to each other because they don't know how to keep the conversation going. If you don't believe that, you should read a book called Alone Together. It was just published by the gal at MIT. Sherry Turkle, thank you. It's a really interesting read. And she says that the teenagers text each other, and they do that because, first of all, it's less data rate than the phone call. But more important, they can not respond. They can take their time responding. Nobody expects instantaneous response. And so they don't feel nearly as threatened by having a person-to-person phone call. This is quite surprising because when I grew up as a teenager, the whole idea was that you talked as long as possible on the phone. This is a completely new generation. We don't do mobility very well in the net. I mean, you could say, gee, look at all the mobiles. What are you complaining about? But the answer is if you move from one piece of the internet to another and your internet address changes, this screws up the TCP connections because their addresses change. And so you can't persist in having these end-to-end connections if the internet addresses change. That was a mistake I made. I thought I was being really clever when we split the internet protocol off from the TCP protocol in order to allow for real-time interaction using the user datagram protocols for speech and video and radar and all that stuff. I thought, well, let's see. Maybe I don't have to have a new header at the TCP layer. I'll just reuse the one down at IP and kind of create a pseudo header and save bits. So I was patting myself on the back thinking, boy, that was a smart move. So 3 decades later, I looked at this and I realized it meant that you couldn't do mobility very well if the IP address changed depending on where you plugged in. And I went back to figure out why was I so stupid. And it occurred to me that to consider the kinds of computers that were around in the 1970s. They were big machines that didn't move around. They were, they were in big buildings and they were air conditioned. And the idea that a machine would get up and walk down the hall or go, didn't even enter my, So I didn't think about that problem, and it was made worse by the fact that we had been testing the packet radio network here in the Bay Area, and Don Nielsen, again, very much involved in that. And so I thought we'd solve the mobility problem because you can move around in the Bay Area with these little packet radios, but they kept one IP address, and there was an underlying routing address that the packet radio system had that kept changing to say how to get to that particular endpoint. What I hadn't thought about was moving from one packet radio net to another with different IP addresses and everything else. So I screwed that one up, and my colleagues didn't point it out, so I'm not going to take all the blame. If we solve that problem, and there are techniques for doing it, today the Internet Engineering Task Force is looking at the ability to segregate the end-to-end identifiers from the underlying routing identifiers. If we did that, not only would it make mobility work better, but it would also allow for what's called multi-homing, because you could be connected to multiple internet service providers assigning different addresses to you, and it wouldn't matter to you how the packets got to you. It didn't matter which ISP delivered it. You would have end-to-end identifiers that said, hi, I'm the same guy on the other end, even though I'm reaching you through different paths. So that's doable today. Most of the things I'm talking about can be retrofitted into the existing network. We don't do a good job of routing traffic over multiple paths to get increased bandwidth if there exist multiple paths between the endpoints, and we could do that too. But the thing that really is annoying is broadcast. We do a terrible job of we take broadcast radio channels like Wi-Fi, omnidirectional Wi-Fi, and we turn them into point-to-point links. And we've not incorporated into the architecture the thinking that if you broadcast something and more than one party can receive it, that could be a really efficient way of delivering a lot of data to a bunch of different people once, instead of having to do it one at a time. So imagine having a satellite that is raining internet packets down on 100 million receivers for information that a lot of people can use. That would be a very efficient way of delivering information. And if you miss some, you could say, hi, I missed packet number 4 and packet number 22. Please send those to me in a unicast way. But all the other stuff would get there in a very efficient way. We should be augmenting the internet protocol space with broadcast-related capability as well. And finally, we have sensor networks, which I'll come back to in a bit. These things have the possibility not only of being sensors, but of being little store-and-forward routers. And so there are commercial systems that create meshes in the radio space, whether it's 802.11 or 802.15.4 or some other radio-based system. You can imagine these sensor systems that are building meshes in order to maintain communication. I'm going to, I realize I'm running out of time. I want you to have time for Q&A. I haven't gotten to all the pieces here, but let me mention authentication, because here's a place where we absolutely did not do very much in the original internet design. It turns out that it's sometimes really important to know who you're talking to on the other end. Whether it's, am I talking to the correct host computer that I expected to get to, or am I having an email exchange with someone I can strongly identify? We did not have available to us in the early stages of internet strong authentication mechanisms using, for example, public key cryptography. It's an irony that public key cryptography was invented on this campus around 1977 by Marty Hellman and Whitfield Diffie. The problem is that 1977 was the year before we standardized the IP version 4 or TCP IP version 4 protocols. So although the concept was around, the implementation of public key didn't exist yet. And so it came too late for us to incorporate into the standards. If it had been more mature, I would have liked to use it. And what's particularly annoying is that in '75, I was working with the National Security Agency on a secured, classified version of the internet. But I couldn't tell any of my colleagues how that worked because most of it was classified, the crypto technology was classified. And so the internet that we're all living with is the one that was unclassified. And of course, looking back on that today, there are techniques that we could use with publicly available technology to more readily secure the network on an end-to-end basis with strong authentication at various layers in the architecture. We could devote an entire day to governance. We're not going to do that. But the thing I want to emphasize is that in addition to all the technology and the possibilities of adding new functionality to the internet, The internet has become so pervasive, even at 20 to 25% penetration globally, that governments care a great deal about how the internet gets used, what people can do with it, what bad things people can do with it, and what threats the use of internet places for especially authoritarian governments. And without making any detailed references to Tunisia and Egypt, you can see that there are governments that are threatened by the freedom of exchange of information which the internet enables. So there are lots and lots of policy issues associated with it now that are of great importance that were ignored in its early evolution. What top-level domain names are permitted? As ICANN opens up the top-level domain space, there are going to be top-level domains proposed that some governments are not going to want to see happen because they will be either politically or religiously unacceptable. Finding mechanisms to allow the debate to happen and allow some resolution of disagreement on what these top-level domains should be isn't, as yet, an unsolved problem. It can't be ignored because names have a great deal to do with culture, with language, with political and social significance. So the governance question is really hairy. Also, we don't have common agreements about what we consider abuse. And until we have some common agreements on an international scale, it will be very hard to deal with somebody who is abusing the internet, especially across international borders. So if harm is done to someone in country B as a consequence of something that country A has done, if there is no reciprocal arrangement between the two countries that this is a bad thing that we should mutually prevent or mutually prosecute, unless we have those agreements, there will be no way to protect someone from harm coming from another country. We don't have those common agreements yet. We don't even have a common agreement of what a digital signature means. How significant is it? If you sign a digital contract digitally and then somebody violates the terms of the contract, is there any legal framework that allows you to go after the party in breach? Well, that depends on whether the country in question or countries in question have reciprocal agreements about the meaning of those contracts. I'm going to skip over a bunch of stuff here. I want to touch on two more things. In the remaining 12 minutes. Those of you who use applications today create fairly complex objects. You create PowerPoint presentations or documents, Word documents and things like that. And these files, these complex files, are only useful if you have software that knows how to interpret them. So now let's imagine that it's the year 3000. And you've just done a Google search, and you've turned up a 1997 PowerPoint file. And let's imagine you're running Windows 3000, just for the sake of argument. And so the question is, does Windows 3000 know how to interpret the 1997 PowerPoint file? And before you conclude that this is a gratuitous dig at Microsoft, it isn't. Even if these were open source standards that were involved, the idea that they would be persistent over 1,000 years, being able to retroactively access and correctly interpret these files is a little difficult to deal with. So I call this the bit rot problem because I'm worried that we will create these complex files and then we will lose the ability to interpret them because the software won't run anymore on the operating systems that we are currently using. A company could go out of business and say, I'm not going to support that format anymore, and you've made a big investment in the software that knows how to interpret those things. So we need a kind of digital vellum. We have to have the moral equivalent of what you can do with vellum, which is to read a 1,000-year-old manuscript today almost as easily as you could read it when it was written. But that's because your eyeball and your brain are able to interpret this. If you rely on software, it's a problem. Open source could help, and cloud computing might be able to help. Because you can imagine if you needed the application to work, it might have to work on a particular version of the operating system. So you might not only need to preserve the application software, but the operating system and maybe even the hardware that it runs on. Maybe you could use virtual machines in order to emulate a whole bunch of that and preserve the ability to still interpret the data. But we don't have any framework in which to do that. There's a whole bunch of intellectual property things that are hiding in that problem. Hi, I'm not going to make this operating system anymore, and too bad if your applications rely on it. And you say, well, can I can I get a copy of the source code of that operating system so I could keep running? And the answer is no, because half of it is going into the new operating system, even though it isn't backward compatible with the applications. So we have no framework right now for really working our way through the problem. So I'm worried that even 10, 15, or 20 years from now, or at least at the end of this century, people in 2100 will wonder about us in the early parts of the 21st century, because they won't be able to read any of the stuff we generated. And so all these digital bits that are rotten. Lots and lots of devices are coming up on the net that I never expected, like refrigerators and picture frames and this internet-enabled surfboard. There's the guys in the Netherlands, and I've never met him, but I have this picture of him sitting on the water waiting, for the next wave, thinking, if I had a laptop in my surfboard, I could be surfing the internet while I'm waiting. So he put the laptop in the surfboard, and he sells it as a product. He's got a Wi-Fi service at the Rescue Shack, and the whole thing is amazing. Now, I alluded to sensor networks earlier, and I have an example of one. I run a sensor net in my house, and I'm very proud of the fact that this is a commercial system. It was made by Archrock, which was acquired by Cisco recently. And they use IP version 6, and they use 802.15.4 underlying 6LoWPAN transmission system, and it's a store and forward mesh network. This is sampling the temperature and the humidity and light levels in every room in the house every 5 minutes and storing this on a little server down in the basement in a rack. One of the rooms in the house is the wine cellar. It's very important that I keep it below 60 degrees Fahrenheit so the corks don't dry out. So that room is instrumented and alarmed. So if the temperature goes up above 60 degrees, I get an SMS on my mobile. And this happened when I was visiting one of the DOE laboratories, Argonne. Just as I'm walking into the building for a 3-day meeting, the mobile goes off. It's the wine cellar calling. It said, you've just broken through the 60-degree barrier. Unfortunately, my wife wasn't home to turn the cooling system back on, so every 5 minutes for the next 3 days, I got a little note saying your wine is warming up. So by the time I got home, it was 70 degrees in the wine cellar, which is not the end of the world, but I called the Archrock guys and I said, do you make remote actuators? And they said yes, and I said, okay, well, that's a weekend project to go put that in. But I needed strong authentication so the 15-year-old next door wouldn't reprogram the house while I'm away. And then I thought, gee, I can see if the lights go on and off, but I don't know what they did while I'm away in the wine cellar. So I thought, what if I put an RFID chip on each bottle? And then I can do an instantaneous inventory, and I could tell if any bottles have left the wine cellar without my permission. But if an engineer friend was debugging this, and he said, you could go into the wine cellar and drink the wine and leave the bottle. So now we have to put sensors in the cork. And as long as you're going to go to that much trouble, you might as well sample the esters that are in the wine to see if the wine is ready to drink. And before you open the bottle, you interrogate the cork. And if this is the one that got to 90 degrees on some awful summer day when the cooling system didn't work, that's the bottle you give to somebody that doesn't know the difference. So you end up with a very useful practical system. We're going to see a lot of this kind of thing in the future because the smart grid program that the Department of Energy and Department of Commerce are pursuing wants to have lots and lots of appliances that are part of the net that can report their status and also take advice about, hey, don't heat the water now, you're reaching a peak load in the electrical system and you can delay the water heater or the dishwasher or the clothes washer. So this kind of thing I think is going to be quite common. So I'm going to just, if I'm permitted, to finish up with a quick update on the interplanetary extension of the internet, and then we'll do some Q&A. Some people, when they hear me talk about interplanetary internet, think I've really gone off my my nut. Are you expecting alien communications? And did you bring your tinfoil hat? Actually, this got started with a team at the Jet Propulsion Laboratory. We were thinking about what was going on in space exploration, Mars being a very popular target. At that point, in 1998, we had already landed the little Pathfinder, which you remember from 1997. There were multiple orbiters around Mars at the time that had been used to map Mars to figure out where the rover should go or where the Pathfinder should go. And they were in the planning stages for the Mars rovers, which you can see some photographs that they were taking. So the rovers, which landed in 2004, had originally were planned to communicate directly back to Earth from the surface of Mars. And it turned out that the radio that was being used for that purpose overheated, and they had to reduce the duty cycle to keep it from doing any damage. And since it was only running at 28 kilobits a second, the scientists were not happy that they were getting even less duty cycle out of that low data rate. By good fortune, though, there were these 4 orbiters around Mars, and a couple of them had the ability to communicate down and up to the rovers on the surface, because the rovers had an additional radio that couldn't go all the way back to Earth, but it could reach the orbiters. And because the distance is so much shorter, the data rate was 128 kilobits a second. The orbiters, since they were out of the atmosphere and had bigger solar panels, were actually able to transmit back to Earth at 128 kilobits. So instead of doing a 28 kilobit transmission with low duty cycle, they reprogrammed the rovers and the orbiters to do store and forward networking by pushing the data up to the orbiter and having the orbiter hang onto the data till it got to the right place in its orbit to squirt the data to the deep space network. Well, this store and forward style is what packet switching is about. It's very much the way internet works. So when they landed the Phoenix lander at the North Pole, which didn't have a direct-to-Earth path anyhow, they just planned to use the store and forward system. So that's how all the data came back from the Phoenix. That's how all the data is coming back from the current rovers, although one of them is stuck with its foot in the sand and is not moving anywhere, but the other guy is still operational. So my partners and I at the Jet Propulsion Lab said, well, you know, this shouldn't be too bad. Let's just use TCP/IP. It works on Earth. It ought to work on Mars, and you know, and it works in the spacecraft. And that was all pretty cool for about an hour and a half, and then we started thinking about the speed of light. And you know, we said, well, let me see. Between Earth and Mars, when we're closest together, it's 35 million miles. If you do the math, it's 3.5 minutes one way, radio propagation. And when we're farthest apart, it's 235 million miles. That's 20 minutes one way, 40 minutes round trip. Can you imagine trying to do, you know, kind of a web application where you hit the key and 40 minutes later the first bit shows up? And I know probably some of you know networks here on Earth that behave that way. But it's not because of speed of light delay. It's for other reasons. So we said, well, you know, what other problems are there? He said, well, you know, when you're trying to communicate with something on the surface of Mars, Mars is rotating, and we haven't figured out how to stop that. So if you try to talk to the thing that's, you know, on the surface and it rotates around, you can't talk to it until it gets back around again. And some of the orbiters are like that, too. So you have not only a variably delayed environment, but you have a disrupted environment. So TCP/IP does not work very well in a highly disrupted and highly variably delayed environment. You don't know what the timeout should be or anything. So we said, all right, this isn't going to work. You know, for those the geeks in the audience, imagine doing a domain name lookup. You're on Mars, and you try to do a lookup on Earth. And first of all, you don't know how long it's going to take to get the answer. And the answer you get back is an internet address. And by the time you get the answer back, the internet address has changed because the thing you were talking to was mobile and it's plugged into something else. DNS doesn't obviously work either. So we said, okay, we're going to have to re-engineer the protocols for this delay and disruption tolerant system, which we did. So we now have a new bundle protocol which deals with these delays and disruptions. We've tested it in some really interesting places. The Sami, the reindeer herders up in northern Sweden, actually helped us test the delay and disruption tolerant networking system by putting Wi-Fi services in the villages and laptops with the DTN protocols in them. And as they wander in and out of the villages, they're dumping data and picking it up. They're like little data mules going from one place to another. Then at one point they were going to hang the transceivers on the reindeer and see, you know, how that constellation would work as a mesh network. We also got the military to help us try this out in tactical communications, and it worked extremely well for their potentially very disrupted environment. The protocols are now on board the space station in several servers. They are on board a spacecraft called Epoxy, which just rendezvoused with the comet Hartley 2 in November of last year. And we're going to be doing interplanetary scale testing during the course of 2011 and into 2012. So we're hoping that these protocols can be standardized and adopted by all the spacefaring nations. My aspiration is that if they will adopt these standard protocols, then all of our spacecraft will have some common ability to communicate, lending the same capability that we get today when we plug into the internet and we talk to 800 million machines. It's just that we would be using these other more resilient protocols. So what I hope will happen, frankly, over time, is that as new missions get launched to explore the solar system, either manned or robotic, if they use the standard protocols and they complete their primary mission, then these spacecraft can be repurposed to become nodes of an interplanetary backbone. So over the period of decades, we might actually accrete an interplanetary system that will support manned and robotic space exploration. So I'm not expecting the aliens to communicate. This is not a search for extraterrestrial intelligence, although you know why we're doing that, because we didn't find any locally, so we're looking at and I do wonder about whether we'll be able to recognize alien porn or not. I mean, did you see the ovipositor on that thing? But I do expect that this has the potential to be quite powerful in terms of helping us improve our ability to give a rich networking capability to space exploration. Okay, so I ran way over. It's 8 o'clock, but I'm happy to spend time doing Q&A if you want to do it. And in any case, thank you very much for letting me be here. Mr. Plummer.
Time for some questions. Please stand up and speak loudly so we can hear you up front.
I've got a microphone here for anybody that has a question to ask.
Happy to run around. Questions?
Yeah,
Sir?
excellent lecture. Thank you. Can you comment on the terrestrial applications, perhaps, for DTN, delay tolerant networks, or?
You mean terrestrial commercial applications?
Yeah.
Absolutely. One of my aspirations is to get DTN implemented in a production version on Android. And the reason I would like that is that mobiles often are disconnected or experience disruption. And I can think of a number of applications where it would be very nice not to worry about that and to have the persistence of the protocol recover from those failures. One of the key things about the DTN is that there's an assumption that the network will store information. This is not the assumption we made in TCP. In TCP, we said the network didn't have any ability to store. So if you can store information on a mobile and it can be part of a mesh, then we could build much more resilience into the system. You can imagine cars having these protocols running, either in the car or in the mobile in the car. My good friend Steve Crocker points out that when he's stuck in a traffic jam in one direction and the other cars are whizzing by, every single car going the other way knows the answer to the question he has, which is, when does this end? And how far is it? And so being able to set up these sorts of very ephemeral interconnections and the like would be attractive, I think. This is one of those examples of enabling things. If it doesn't, the ability to do the DTN doesn't do any particular application, but it enables things that are resistant to or overcome disconnections and arbitrary delay. So I can't give you an application-specific thing, but I believe having that capability would enable some really interesting ideas. Right over here, yes.
I know you credited openness as a part that caused the internet to flourish. What's your view on the platforms that are currently being created, such as Facebook, which is really closed? You look at Google App Engine, the APIs are there, but they're very closed. What do you think that's going to do to the future of the internet? Okay.
So I think that the Facebook situation and the App Engine situation are not exactly the same because as you point out, the APIs are open. And the important thing is that you be able to move from one platform to another. So we need more standards that would allow this kind of motion. That's why I was talking about cloud-based systems having more open standards that will allow people to move from one place to another. The same argument should be made for the application space as well. Facebook it's an interesting environment because it reminds me a little bit of the AOL environment in the early days of pre-internet. It hides, in a sense, it hides information from the rest of the world. You have to be part of the Facebook environment in order to get access to it. The consequence of that is that it can't be indexed. It can't use the normal search mechanisms that the open World Wide Web offers. And I think the side effects of that are, of course, that you won't be able to find things as readily unless you're part of the Facebook environment. I don't know to what extent that will be either an attraction or a distraction. If you want the ability to search over a much broader range of things, and then imagine having to do a search in each different closed environment to find things. The ease with which we find information today is a consequence of the ability of the crawling systems to cover a great deal of information. So my sense is that if the closed environments dominate, then a lot of the flexibility and convenience and power that we've had from the internet will dissipate. And I'm sort of hoping that the general public will discover that that's an issue. I can't predict, of course, what's going to happen, but I can say that the analog of this were the proprietary protocols of networking, the SNA and the DECnet and so on. Those companies actively, by policy, resisted non-proprietary protocols and eventually were forced by the users to implement them and make them available. So I don't know whether the same forcing function will arise out of the closed network environments that we're starting to see arise, but I hope that the forces for openness will win because the utility has been so dramatic. So, you know, if you have a couple of ideas for undoing the closedness, you should think about making that happen. Other questions? Way in the back here. This is part of my health plan. Yes, sir.
Other than the laptop and the surfboard, what has surprised you the most and surprised you the least about the development of the internet?
The biggest surprise for me was when the first one, of course, was when the first graphical web interface came along from Mark Andreessen, the Mosaic implementation. The stunning fact that the internet could be visual as well as textual was a big surprise. But the next big surprise was the willingness of so many people to put information into the net that they didn't expect any remuneration for. They had no pecuniary motivation. They simply wanted to know that the information they shared was of use to somebody else. And I had no anticipation that there would be so much desire to share that information and make it accessible and useful. And it's possible that a lot of the things that we see today are driven exactly by, well, it could be exhibitionism, but it's also, I think, this desire to be useful, of use to others. So that did surprise me a lot. In terms of things that surprised me the least, I guess because of the experience of the ARPANET and the applications that were running in it, email being invented in 1971, the online system from Doug Engelbart was already there and quite powerful and useful. Some of the applications were not a surprise. It just took a while to get there. When Xerox PARC was doing the Alto machines and building Ethernets that were running at many, many times faster than the backbone of the ARPANET, they were living 20 years ahead in the future. And I think anyone who could see the possibilities could envision what was going to happen. The part that I had difficulty with was realizing that the cost of these things would drop so much. The Altos must have been $50,000 each, John? Something like that. And, you know, to imagine that you would get to the point where an ordinary mortal could pay for that out of their, you know, salaries, but it's $100 or a few $100s. I had trouble fully ingesting. But nonetheless, you could see the seeds of that evolution coming out. I'd be interested in what other people who've been around for a while were surprised at, too. I know, John, did you have anything that specifically either surprised you? Or this is John Schock, by the way. He's very involved in the Xerox PARC and the STAR and a lot of other venture things now. But do you have any specific things that either surprised you or didn't surprise you?
Well, the one thing which you referenced to in passing, and it's a line that I've used, is, and I'm several decades too old, that I continue to be stunned about how much information people are willing to share. And there is this symbiotic, you know, the sadist needs the masochist, and so the exhibitionist needs the voyeur. And I am completely of the wrong generation. And I have no Facebook account. I have no LinkedIn account. I completely refuse. And I know I am just sort of antediluvian on this, and the world has passed me by completely. And, you know, I battle with my kids, I battle with everybody I know, and it is, you know, we clearly knew about document sharing and printing and resource sharing and email. We could sort of see that whole path. But this whole notion of the willingness to share and want to share information, and it's just not in my DNA, and there's a whole new generation of technical capabilities and social stuff that is just continues to astound me.
So if I could, this is sort of DNA meets DNS, right? You will appreciate, if you haven't seen this, those of you who are, let's say over 55 or 60, if you do a Google search for the battle hymn of the baby boomers, you should go find that and listen to it. It's about 2.5 minutes long, and it's absolutely hilarious. It's written to the battle hymn of the Republic, and the refrain somewhere in there is "We pissed our youth away," and that's part of our problem. Okay, go ahead.
What is it about the cloud that makes it different? If you send something to the cloud, and you said the clouds can't talk to each other, whereas in other situations, I think you can.
So the problem here is that the cloud presents a client-server kind of interface, but what it doesn't offer is a server-server interface. And so that's right now the clouds would see each other at best as simply a host or something on the internet. Some of my friends who do cloud stuff hate it when I say clouds are sort of like time sharing on steroids. That sort of minimizes or dismisses some of the incredible power, the flexibility of the cloud, the ability to scale up and scale down and store huge amounts of data and process it and everything else. So I don't mean to diminish anything here. But the fact is that they still are presented as a web-based client-server structure, and that's not the best means through which the cloud should be interacting with each other, in my opinion. But again, we don't have standards for that, so we won't know until we start experimenting with that stuff. Okay, I think we have time for a couple more. Let me get this gentleman here and then back here.
I think the internet was invented especially for the wireline network. That's what TCP/IP, especially for the wireline network, right? But right now the internet goes to wireless. More internet goes to wireless, mobile phone, whatever should be there. So when the openness goes to the wireless, we have to talk because traditional the wireless communication is very radio oriented, especially based on the GSM, based on CDMA, whatever. It's very close architecture. So when we move the internet from the openness from the wireline to the wireless, there we have to solve the open wireless architecture in the transmission side. So that's the issue there. So what do you think about the issue?
Okay. So first of all, let me disagree with your premise, because the three networks that were used to drive the architecture of the internet were the ARPANET, a wireline network, the Packet Radio Net, a wireless CDMA mobile network, and the Packet Satellite Network, which is a multi-ground station dynamically shared satellite channel network. So wireless was absolutely a part of the internet architecture. The part that was missing that I mentioned before was the ability to understand what kinds of things would be mobile and how their addresses would change. So that's one thing. The other thing is that recently there's been some discussion about public safety and public safety networks, and the direction that they seem to be heading in is LTE, which is a cellular style design. And I'm actually uncomfortable with the idea that the emergency network is dependent on a system which is often known not to work during emergencies. Or if the emergency occurs in a place where there isn't any cellular infrastructure, base stations, backhaul, and everything else, it may not work. So I actually like the idea of going down a different path, which is a mesh-like thing which can be ad hoc. You have issues about who can join and who can't. There's authentication and access control. I don't mean to minimize any of that. But I also rather like the idea that everything that's transported in that system is IP-based. And it's not because I'm in love with the internet protocol. The part that I like is that it doesn't care how it's carried. It doesn't know what it's carrying. So it could be voice, could be video, it could be sensor systems and everything else. The network is oblivious to any of that. And by the way, the police and the emergency medical responders and the police department and the fire department today have a lot of trouble communicating because their radios have to work at RF. If instead we said, look, the whole base here is IP, and if you need to communicate by voice, we're going to use voice over IP, And we will, if we have to, we'll do RF transformations in some, portable nodes. But the whole idea is your compatibility on an end-to-end basis is based on voice over IP, not based on radio compatibility. We'd have a much more general architecture. But for some unknown reason, that obvious fact has been resisted or ignored by an awful lot of the public safety environment for reasons I don't fully understand. You had a question.
Thank you. So a couple of things you were touching on when you were talking were about some of the mistakes that you had made, but also some of the very good design decisions you had. And in some sense, it's really remarkable that you built a system that right now is being used for things that probably would be way beyond what was even technically feasible in people's wildest imaginations many years ago. What I'm curious about is, do you have any tips or advice on how to design a system knowing full well it's going to grow beyond anything you could possibly imagine, or to be used in ways that would be, sorry, that was not meant that way, but,
right.
but
Yeah. Okay, so first of all, let's make sure that everybody in the room understands that it's not just me. I want to make sure that you appreciate that this is a collaborative effort, and the secret sauce was making sure that anybody with a good idea could be heard and could participate. The IETF is like that. The early architecture work had lots of people contributing to it, so I don't take a lot of credit. By the way, for those of you who have kids, it's important life lessons. Don't take too much credit when your kids do well, because you'll have to take credit when they screw up, or accept blame when they screw up. So just be very thoughtful about how much credit you want to take. I think the honest answer is, don't try to overspecify the system that you're building, because every overspecification I can think of involves assumptions, and those assumptions on a system that has any longevity at all are guaranteed to be wrong. And so by not overspecifying, by leaving a lot of room for other choices to be made, you create a lot of flexibility. I'll give you a rather odd example of this. Americans often go to Chinese companies to get things built, and they often specify in extreme detail exactly what they want. I used to work on the board of a company that did optical materials, and they had a Chinese manufacturing operation, and they specified in great detail exactly what they wanted. They knew how they were going to test the resulting materials and then do the final assembly, and they got back exactly what they had asked for at a certain price. I happened, by some happenstance, to discover another company in China that was using the same producer, and learned a little bit about the specs that they were offering. And their specs were looser in the sense that they didn't specify exactly everything. The consequence of that, let's say, freedom, allowed the producer to come up with better ways of making the product at less cost and faster. And so the side effect of all this was that the flexibility and the lack of specificity allowed for some freedom. And it's actually quite an important notion. So here's something where you have to get the level of specification right to allow yourself to have this flexibility to recover. Let's do one more. It's already almost 20 minutes past the hour. This gentleman, there's a lady way in the back. So I'll do two. I'll do you, and then you'll get the last word, okay? Yes. That'll get me halfway out the door, but
with the dispute Netflix has had with Comcast lately, and then Comcast is apparently going to buy NBC, which gives them a strong competitive reason to shut out Netflix. In 3 to 5 years' time, how are we going to have internet access where we can get to whatever we want?
Well, that's a good question. And of course, the FCC has been trying to argue that there should be some rules about openness and some inhibition of taking advantage of the underlying carriage to influence the applications above that level. That's going to be both a potential legal and certainly a commercial debate over time, and I can't guess exactly how this is all going to come out. But if the FCC rules are applied, there will be the question then will be, by what mechanism does an unfairness, if that's the conclusion, how is that unfairness dealt with? I frankly hope that there will be strong enough incentives to avoid this sort of abuse by controlling application space because of what the underlying transport. On the other hand, another possible thing to happen would be that somebody will recognize that this is an issue and find a business model that allows additional competitive access to be provided. Up until now, that hasn't been the case. There aren't very many choices that we have for broadband access. It's a fiber system, it's DSL, and it's cable, and that's about it. And in any one place where any of you live, there might be a choice of two, which doesn't necessarily generate a lot of competition. Ultimately, if it's arguable that there is a restraint of trade, I would assume the Department of Justice would have to step in to make an argument that that's not an acceptable practice. I think we're still in uncertain territory right now to see how that works out. Let me get this last question, and then we can all have a break. Jim can tell us where to go.
Actually, we were streaming this live, and this question came from Twitter, so I feel obligated to ask it.
From France?
No, from Twitter. I don't know where it came from. It was just via Twitter.
Okay.
When would be able
from
to...
Twitter. I thought you
Right.
said Trier. And I went, okay, fine, Twitter.
My accent is...
Yeah, that's all right. No, that's all right.
When will we be able to move virtual servers across subnets and countries without resolving IP addresses?
Well, there's an interesting little technical thing. Well, if you use the DTN protocols, you wouldn't have to worry about resolving IP addresses because we don't do DNS and all that stuff. I think the answer is that isn't the problem. The problem is not resolving the IP addresses. The problem is having protocols that are insensitive to changing IP addresses. So the answer, at least in the Internet Engineering Task Force space, would be Lisp or some of the other protocols that try to insert a shim between the IP layer and the higher level protocols to isolate them from changing IP address space. Jim, I'll turn this back over to you.
Thank you. So we have...
Thank you.
So we have refreshments in the lobby directly behind you. We'd encourage you to stay around for a little bit and catch up with old friends or try and catch Vint and ask him some more questions. He will be with us for a little while longer. Thank you again.
That sounds really scary. Do you know something I don't know?